Can you see the screen?
Yes, perfect.
Would you do another or third? Would we do it back?
Yeah, that would be good. Let's just keep some extra minutes.
Yeah,
That's exactly what I wanted for. Just in case someone else is jumping into the range. Oh, I'm really turn out the. Yeah, we can also do the audio. As long as this mic is open. Yeah, because we can hear you from the record.
Then that's easier if you.
Yeah.
No, I will just be standing.
Yeah, it goes in your computer.
Yes, I moved it.
This one's a bit forward as it was.
Let's do it.
Okay, good afternoon, everyone. I am very happy to see that there is quite a big crowd online. So greetings to you all. It is also a pleasure for the Cybersecurity Masters program at Tech to have today Dr. Thijs van Ede, whom I will introduce briefly to you. Dr. Thijs van Ede is an internationally recognized expert in cybersecurity and artificial intelligence, with extensive experience in applied research in security event analysis, anomaly detection, distributed system protection. He holds a PhD in computer science from the University of Twente, where he currently works as an assistant professor in the Semantics Cybersecurity and Services Group. His research has been published at prestigious conferences such as IEEE S&P, NDSS, and CCS. He also has collaborated with international research centers such as the SEC Lab at the University of California, Santa Barbara. So without further ado, Thijs, the floor is yours.
Well, thank you, Harrison, for this nice introduction. And thank you all for joining in such large numbers. It's good to see that. I want to start off by saying pura vida. That's some of the Costa Rican Spanish that I learned while being here. Unfortunately, that is the only Spanish that I've learned. So the rest of the talk will be in English. But let me, well, besides what Harrison already mentioned, introduce myself very quickly. My name is Thijs van Ede. How do you pronounce it is a question that many people ask. If some of you know this person, Mike Tyson, it's pronounced like his last name without the O-N part. So Thijs, that is how you pronounce my first name. As Harrison already mentioned, I am an assistant professor in the field of AI and cybersecurity at the University of Twente. And I do my research in the Semantics Cybersecurity and Services Group at that university. Now, the University of Twente, where is that located? Some of you might wonder. Let's first take a map of the world. Big map. First, it is in Europe. So this part of the world, if we zoom in a little bit, we can find the Netherlands. And within the Netherlands, we are located on the east side, so very close to the border with Germany. This is a quick picture of the campus that I work at, very green, as you might see. And this is a picture of the research group. So I'm part of a larger group of people doing research and teaching in cybersecurity. But let's get to the topic of today's lecture. And that is titled Terminator, Using AI to Mitigate Cyber Attacks. That's a very flashy name, and I hope that I will do it justice. But before we dive into the actual contents, I want to give a little bit of a background. So what we will be focusing on today is mitigating cyber attacks. And that is usually something that is done in the field of security operations. Now, what is security operations? Suppose that we have a network of computers, for example, all devices present at the university. And one of these devices gets infected with a virus or some malware. Well, of course, we don't want that to happen. We want to get rid of this malware. So what do? Well, first, we install some agents. This can be virus scanners. It can be endpoint detection points. And these agents, they collect activity that happens on all of the devices that we monitor. So for example, we will collect some logs saying, we have this program, in this case Firefox, who opened a specific file, in this case the etc shadow file. And we might have a network connection going from this 192 IP address to the 8888 IP address. And that network, that traffic or these logs are being collected and they are sent to a intrusion detection system. And this intrusion detection system has either some rules or some machine learning or artificial intelligence running on it that try to analyze this activity that is captured in the log files and try to find suspicious activities. So one of these rules that might be present is, okay, if there is a file access to this etc shadow file, which on Linux is the file containing passwords or hashed versions of passwords of users, we might want to trigger what is called a security alert. Now, if this rule matches, we basically take this security alert and we send it to what is called a security operations center. And the security operations center takes in all of these specific suspicious events, and they will have to deal with those. This can be manually or automated. Current practices is that a lot of the stuff that is done in these security operations centers is done manually. And in this talk, we will be looking at how do we automate this process using artificial intelligence. Now, what is actually happening in one of these security operations centers? First of all, when these security events arrive, a person has to make a decision of whether this suspicious event actually constitutes something malicious or whether it can be seen as something that has happened but is not necessarily interesting from a security point of view. Now, how does this work? For example, take a faulty login. Suppose that you want to log into your university account. You accidentally mistype your password. Well, that might be something suspicious because it could be someone who is trying to enter or crack your university account by just trying lots of passwords. Or it could be something where you say, I accidentally mistyped my password once, but on the next try, I succeeded. So I can validly log into my university. Well, the job of this person here is to triage events, basically deciding of whether a security event like the one I just showed you is malicious, so whether it's part of an attack or whether it is something that we can ignore. So once this decision is made to either discard an event or to really create an alert from it, this alert is usually escalated, and that means that the alert is investigated. So a security professional will look at the alert, try to figure out what kind of attack is going on, and then subsequently they will come up with a response plan. And this response plan could, for example, be something like we lock down the account of a user, or in case of a DOS attack or DDoS attack, we try to block some IP addresses from the firewall. Depending on what type of attack is going on, a specific response plan is thought up and implemented. Now, as I mentioned, this left side of the security operations, the detection, is already largely automated. But this right side, the things that happen in the security operations center, is largely done by manual effort. Now, what is the problem that this is done manually? First of all, manual analysis is slow, right? We have to have a human who investigates all of these different alerts. Humans typically take their time in order to understand what is going on, in order to make sure that they really know what kind of plan to implement. And that is a problem, right? Because as we have an attacker attacking our system, the longer the attacker has access to our system, the more damage they can do. So the sooner we are able to stop such an attack, the less damage they can do. Next to that, it is also very expensive to do this manual analysis. Well-trained security operators are scarce, which is, of course, good news for the students that are going into this direction, like most of you are. But it means for organizations that it is very expensive to pay all of these people to look at this kind of data. And lastly, the job of a security operator can at some times be quite boring. The automated data that is sent to the security operating center often contains what are called false positive alerts, meaning that these are alerts for types of events that are not necessarily malicious. And having to filter through tons and tons of these events can be quite boring and can be quite mind-numbing. So we want to make sure that we can offload many of these tasks to automated systems. So that brings me to the topic of my talk. What if we have an idea? Let's create an artificial intelligence to mitigate actual cyber attacks and to make sure that the operations that are currently done manually can be automated. And to make this a little bit flashy, I thought about the title. I thought, let's call this AI the Terminator. Because just like in the movie, we want to stop, malware from happening. We want to terminate it. But also just like in the movie, we should make sure that these terminators do not go out on the loose and cause more damage than we initially want. So let's think this through. What is the Terminator supposed to do? The Terminator should mitigate cyber attacks, but the Terminator should not negatively affect systems or users. So if we are attacked, we want to make sure that this Terminator AI is able to pinpoint this is part of the attack. So this is part of the system that we should isolate or make sure that no further damage is done. But if there is not really an attack going on or there is a false positive, we should make sure that this Terminator AI does not negatively affect the users by, for example, closing someone's account in case someone logs in with the wrong password once, right? So we need to do a couple of things in order for this Terminator AI to exist. First of all, we need to ask ourselves what actually constitutes a cyber attack, right? We want to know what kind of behavior this Terminator should be focusing on. Because if we do not focus on the right type of behavior, we might cause negative side effects. Second, we have to make sure that this Terminator indeed triggers the right kind of actions. So suppose that someone is trying to log into your account, we want to stop the login attempts, and we do not want to shut down the system completely. And we have to think about what kind of safeguards we can build into this Terminator so that it doesn't go out on the loose. Now, let's dive into what is a cyber attack. And for that, I'm going to talk a little bit about tactics, techniques, and procedures, also known as TTPs. Yes. Does this work? Perfect. All right. Tactics, techniques, and procedures, also known as TTPs. What are they? They are terms in which in cybersecurity we often use to describe how an attacker penetrates a system. Where tactics indicate the goal of an attacker. So for example, the goal of an attacker could be to exfiltrate some data, to steal, for example, financial records. Another goal could be to put a denial of service attack to make sure that the system is not available anymore. Or a goal could be financial theft. For example, in case an attacker wants to put ransomware on your system and then try to extort you, right? These are goals of the attacker. We describe them as tactics. Techniques are the ways to accomplish such a goal. So for example, if we are looking at data exfiltration, you can do that over a USB stick by plugging it into a computer. You can create a botnet with a command and control center that tries to communicate with infected machines and therefore steal some data. There are very many techniques that you can use to accomplish a certain goal. And then we have procedures, which are concrete implementations of the technique. For example, the Kabalos malware can be used as a command and control channel to exfiltrate data or credentials over the network. And in this specific case, Kabalos uses the UDP protocol. Now, these tactics, techniques, and procedures are captured in many different ways, But one of the main ones is via the MITRE ATT&CK framework. Some of you might have used that if you already work in a company. And the MITRE ATT&CK framework basically takes these tactics, techniques, and procedures that have been observed out in the wild, and they try to create a sort of knowledge graph or knowledge database that connects which specific attack groups, for example, people from North Korea or Russia, use which different software to implement the techniques, and which techniques are then related to tactics. What is also important is that this MITRE ATT&CK framework suggests some mitigation strategies. So in case you are attacked by a certain technique, they provide mitigation strategies in order to make sure that you know how to defend against such an attack. So in short, MITRE ATT&CK provides external attack information for security operators. Using this information, they can make, as humans, the right decisions on what is an attack or what is not an attack. Now, of course, this is what humans do. And we want AI to take over this task to make it more efficient. So how can we use this knowledge to automatically try to identify what constitutes an attack and what doesn't? And therefore, I want to look in how we actually can identify attacks and triage the security alerts that we just saw. So how can we make sure that we know which security alerts are true positives that we need to investigate and which ones are false positives that we can discard? Now, let's go back to the previous example that I showed you. Suppose that we have some devices that are being monitored. So we collect some logs. They are being sent through an intrusion detection system that produces the security events. We want to make sure that the work that this operator does, the triaging of events, either discarding them or escalating them to a higher up, is automated. So the challenge that we are looking at is, can we automate security event triaging such that our Terminator system can focus on real attacks and not deal with any kind of issues in case someone, for example, forgot their login credentials. Well, me and my research team, we basically wrote a paper about it, and I will briefly discuss what this paper was about. And for that, I will first give you an intuition of the idea that we had. So our main idea of this paper was that if you look at one single security event, it does not say a lot about the potential threat to a system. However, if you look at other security events in the context of an attack, it might tell us a lot. Now, let me illustrate this with an example. Suppose that we have a machine, and that machine triggers a security event that says that beaconing activity is found. What is beaconing activity? It is basically a periodic connection to another server, and this could indicate a couple of things. Beaconing is usually found in malware that tries to communicate with its command and control server. And if that's the case, we want to shut it down, right? Because we don't like malware on our system. However, it could also be a benign application that is just doing a periodic check for updates, right? And if we just look at this beaconing activity, we cannot distinguish between the two. So what do? We also look at other events that were surrounding this beaconing activity. So suppose we are in the following scenario. We have the same computer and it accessed a recently registered domain. Could be something suspicious, could not be. Afterwards, it downloaded some data using a self-signed certificate. Then we found a packed executable. And afterwards, we found beaconing activity. Combining all of these alerts, it is very likely that it's some malware that phones home. Because why would you otherwise pack your executable or if you are a legitimate application, why do you use a self-signed certificate? Now, this is the intuition that we used to make an automated AI system that can actually perform this triaging for us. And this automated AI system we called DeepCase, which stands for Deep Contextual Analysis of Security Events. And the idea is as follows. What if we just let the normal security operator do their job? We ask them to triage these events based on their context. And they will say, this is something that can be discarded, or this is something that should be escalated. And then once we do that, we register all of these decisions in a database. If we have a large enough database, we could say, hey, what if we find a similar event in a similar context? We can just copy the previous decision that the security operator made. And if we find something that is not similar, well, we simply show it to the security operator so that they can make a decision, and we add it to our database. Now, of course, in order to do this, we need to have a notion of what is similar, right? And this is not necessarily enough, because we found out that a lot of contextual events are irrelevant if you are identifying an attack. So suppose that an actual attack is going on and Alice forgot her password in the meantime and is trying to do a login attempt, failed login attempt, then that failed login attempt is not necessarily related to the actual attack. So how do we filter those kind of spurious correlations out? And of course, as the beginning step, we need to first of all collect all of the events. So let's have a look at the DeepCase system and see how we did this. Well, for the security events, we simply took all of the events that were produced by a specific machine, and we put them into chronological order. And then we say, okay, we want to look at a security event and the context. And the context is basically any security event that happened before the security event that we are investigating, right? So we have an event, we have its context, and together they make up the event sequence. And what we can basically do is create a sliding window over all of the events of every machine that produces events. Now, we want to make sure that we also deal with irrelevant contextual events, right? In this case, I've just made a schematic where we have red events that are related to the attack and green events that are accidental events that are triggered. And we want to make sure that we, for our similarity, only focus on the red events. Now we need a way to automatically analyze this context to see which events are related to the event under investigation. How did we do this? We used an algorithm, in our case, a recurrent neural network, to look at the contextual events and based on those events, try to predict what the next most likely event is going to be. And if we feed this with a lot of events, eventually our AI algorithm, our recurrent neural network, will be able to say, based on this context, I will likely expect this event to happen next. Because if we see a lot of attacks in a similar context, we say, this is a context that we've already seen. So we likely think that the next step of the attacker is going to be this. Now, what we did with this AI is we built in a mechanism called the attention mechanism. This is something that is also used in big AI systems like ChatGPT, for example, which I will talk about later in this talk. And this attention mechanism allows us to take a look into this black box of an AI. It basically allows us to see what the artificial intelligence focused on in order to make its prediction. And this is something that we used to say, suppose that we correctly identify this E12 event as a predicted next event. what events in the context did the AI system focus on in order to make this prediction? And if we know that those events are likely going to be related to the attack that involves E12. So if this is the case, they are correlated with the prediction. We basically say, these are the events we identify to be relevant. Now, if we've identified the relevant events, we want to make sure that we can compare these with other contexts and events to make sure that in the future, we can see, if a specific attack happens in a specific context, we know that we can copy the decision because it was similar to something we previously saw. And we did this through what we call the interpreter. And the idea is that we group together alerts from using similar event sequences. Now, when are these event sequences similar? If the attack happened in a similar context. And how do we measure this? We measure this through the similarity in the correlated events, so from the previous step. And in our case, we used the Manhattan distance, which is a computational distance to give a measurement of how similar a specific attack in a specific context is to something that we saw before. And we can use this distance to cluster together events that are similar. Now, if we make these clusters, of course, we want to know how well this procedure works. So what we did is we reached out to a company called Lastline, which was later acquired by VMware. And we asked them, hey, we know that you have a lot of data from a lot of different companies. Can we use this to run our system on and to basically perform alert triaging side by side with your security operators? We did this over a period of 6 months with 20 of the customers of Lastline. We collected over 10 million alerts, so we had a very large data set to run our system on. And we used it to automatically escalate or discard known alerts and to manually inspect new alerts. Now, how well did this system actually work? For the manual analysis, we performed an analysis to see, okay, if we have a cluster of similar events, how likely is that cluster to be malicious? So we asked the security operators to triage some of the events in each of these clusters. They sampled some random events for manual analysis, and they classified them into 5 different risk levels, from information to low, medium, high, and something that has been a verified attack. Now, for a lot of these clusters, all of the risk levels were the same that the manual analysis was done on. However, for 14.5%, there were some varying levels of risk in the same cluster. And this is going to be a slight problem, because if you say, this cluster, so these kind of attacks have a specific risk level, they are high risk, but there are also some low risk events in them, then apparently they are not similar enough, right? So we can't necessarily copy the decision. Well, we basically took a safe approach and we say, okay, if we have one of these clusters that has varying levels of risk, we always assume the highest risk level. So if there's a high risk level, we simply say this must have been part of an attack, so that at least we know that someone will have a closer look at it. And what we found is that if manual investigators only look at 10 events per cluster, we already have a confidence of finding a suspicious cluster of 84.5%. So that means that if a cluster contains 1,000 events, only 10 of them have to be analyzed, which reduces the workload of these manual operators by a lot. In fact, by inspecting only 10 samples per cluster, we reduced the manual triaging workload by 95%. So operators became a lot more efficient when using this deep case approach. Now, besides manual analysis, we also looked at the automatic analysis. So let's take a step back to our evaluation. We found out that for automated analysis, 86% of the sequences were similar to the ones that we observed before. And combined with the manual reduction in workload for new alerts, we found that the overall workload of security operators was reduced by 90%. So that means that instead of having 10 security operators, you only need 1 to do the full job. What we also looked into is there a chance that we may underestimate the risk of a security event? Right? Because if our automated system is reducing the workload by 90%, that sounds great. But if that means that all kinds of attacks will pass through, unfortunately, we only underestimated the risk in 0.001%, which of course still translates, especially if you look at 10 million alerts, to, I believe, in the order of 20 or 30 security alerts that we missed. But this is a kind of a trade-off between having a reduced workload, so being able to automate this triaging, versus missing some of the actual security events. So, in conclusion, for this first part, with the deep case system, we were able to reduce the workload of security operators by 95% in the case of manual triaging, and by 90% in case of automatically dealing with events. And we underestimate the risk in less than 1%, 0.001% of cases. If you think, hey, this is something interesting, the code for our work is freely available online, and so is the paper. And with that, I would like to end the first part of this presentation and open the floor up for questions in case there are any regarding deep case or security alert triaging.
Si hubiese preguntas, porfa, me dicen o la escriben por el chat. Vamos a ver.
Hello. Thank you, Thais, for your presentation. How are you, Gerson?
Maybe you can open the sound in your computer so that you can
That
listen
is
the question.
connected to the speaker, and I'm not sure if that's...
Let's try.
Yeah.
You hear me?
I saw that Saul had a question. Can you please ask the question?
Yes.
And let's see
Sure.
if that actually
Well, thank you for the
works.
presentation, Thais. Can you hear me?
At the moment, I can't hear the question.
Can you hear him?
Or what about now?
No.
Maybe I can
Let me
write it.
see if I can change the audio output.
I do hear you, Saul. If you want, you
Okay.
can.
Okay, I can tell you, and then you can
I will
say
repeat
it
out
again.
loud.
Okay, cool. Yeah. So I just have a couple of questions. I wanted to know exactly how did you train the model in the first step? Because what I understood is that you do train a model for the prediction of the next event.
Okay, give me a sec
So,
because otherwise I forget. He's asking how did you train the model in the first step? Yes, that also could be useful. Maybe I can bring the microphone and put it in the
Yes.
speakers here. Give me a second, so sorry.
Sure, don't worry.
Okay, let's try again.
Yeah. What about now? Can you hear me?
So.
Not very well.
Okay, the
Well,
question
I give it a
was
try.
how did you train the model? What else did you say?
In the first step, Yeah, the
In
model
the
for the
first
first
step.
step.
Do you remember the slide number? Maybe no.
Yeah,
I will
let
go
me
to the
just.
overview.
That's the one from there. Yeah.
Here,
Yeah, that's the one.
the step A.
Mm-hmm.
So
In the first step.
in step A, we didn't train a model. We simply collected the events. But in the context builder, so step B, we basically created this AI model that tries to predict what is coming next. And what we did in the end is we took the data from last line, which was collected over 6 months, and we took the first month of that data. So I believe it was January until beginning of July that we collected the data. And we took the data that we collected in January to basically create these sequences. So we simply ordered the data per device and then ordered it in a chronological order. And we fed it through this AI system where we basically gave the context as input and the target output was the event under investigation. And by observing a lot of these contexts in combination with the target output, we could train this model to try and predict the correct target output based on the context. What we did next is we took the other 5 months, so February until beginning of July, and we fed it the new contexts and events under investigation. And when we did that, we basically took the context and tried to check, okay, is the event that we predicted indeed the event that we actually observed? If that is the case, then we basically are in this scenario and we follow the rest of the methodology of deep case. If that was not the case, we did a smart little trick where we say, okay, suppose that you have to predict this specific event. What kind of combination of events in the context would be the most likely to output this event, to predict this event? And then we would have used that as the context or the relevant events in the context. And the rest of the system actually doesn't really use much training because the interpreter only uses a distance function, which allows for clustering. And clustering is an unsupervised process. So you only need to have the data, but you don't necessarily need to train anything for this. So that is basically part of how we trained this deep case model. Does that answer the question?
Yeah, sure. I just have another question. This one is more simple. Is the dataset that you use available? Is it open? Or what other datasets can you use to test a system like this, like a similar one?
Okay, second part of the question. Okay, this was good, but the second part of the question is if the data set that you use is open, or if not, what kind of other data would be possible to use to perform a similar test? Was that correct? Is fine. Telephone Churchill good, okay.
Yes, regarding the data set itself, unfortunately, because Last Line is a organization that looks at real-world attacks, we were not able to share the data with other people. So we obtained this data under an NDA. What we do have is 2 sets of experiments in our paper. One is with the Last Line dataset, which I presented to you, which is the cool real-world experiment. Another one is with the HDFS dataset, which is a dataset that is available publicly, also via our link on GitHub. And this dataset basically contains anonymized sequences of events that have been labeled as being anomalous or as being benign. And this dataset can be used to validate the results of deep case. But of course, if you want to do this in practice, we always recommend to try and work with a real-world dataset if you have access to that. Does that answer your question?
Yes, sure. Thank you.
All right, then I also see a couple of questions in the chat. And I have the chat here open so I can read them out loud. Could you please share the presentation? Yes, I will send the PDF version to Harrison afterwards, and he will then share it with all of you. Then by Hernaldo, are there mechanisms in place to manage the legal and ethical risk of automated profiling, particularly regarding user or customer rights such as privacy and non-discrimination? Or is this intended to be used only with open and public data? That is actually an excellent question. When we were performing this study, we basically contacted the customers of Lastline to see if they would be open to be in this pilot study. And they voluntarily agreed to let us run this analysis because in the background, there were also manual security operators that were still triaging these events. So there was always a fallback mechanism in case our decisions that we made using this AI were incorrect. However, so far, as I am aware, there are not that many legal regulations in place yet that actually guide the uses of AI. I know that in Europe, we have the AI Act that is coming this year, which basically states that any type of AI should be free of bias, as well as the party responsible for the decisions lies with the party that is actually using this AI. So in this particular example, it would be Lastline that would be using this AI. So customers of Lastline could hold Lastline responsible in case that the AI is making an incorrect decision. So are there regulations in place? I know that in Europe, they are trying to build this AI framework. In the rest of the world, I'm not 100% sure whether this is already in place. Because that is not my area of expertise. But in general, what I recommend is that when you run these systems, always make sure that you have a backup in place where you can have a look at some of the events that are discarded automatically and try to verify whether the system is actually working correctly. And I think that I hope that answers your question, Hernaldo. Perfect. Then I see that Sebastian also has a question, whether this approach is suited only for batch analysis or whether it can handle real-time data in streams. And that is also a very good question. So what the setup of this system looks like is that in the first month, when we are training this context builder part of the system, we have to train that in one go. However, because this is a recurrent neural network, we can continuously update this network. So after it has been pre-trained, once we have new data, for example, of the 5 months that we had in our test scenario, we were continuously using this context builder system while also updating it in real time. We did that in batches of, I believe, 32 events sequences. But you could theoretically also do this in batches of 1 event sequence. Now, the other parts of the system, for example, the interpreter, is doing clustering. And clustering is something that you can also do in real time. Because once you have a couple of clusters, you, of course, need to wait a little bit before you have enough data points to form a cluster. But once you have a cluster, you can simply continuously add new data to that cluster. Now, of course, if we find a new data point that will not be classified into one of the existing clusters, we simply put that data point to one of the security operators to do the manual analysis. However, if that manual analysis has been done, we store that in our database. And once new points start to come in, we ask the security operator to still identify whether these clusters are malicious or not, or what their risk level is. And at one point, there will be enough data points that will form a new cluster. And once that new cluster is formed, we can basically take the risk assessment of that cluster. And if new data points get added to that cluster, we can simply copy that as well. So does it work only in batches? Not completely, but it has a sort of startup time for the system to work. I hope that answers your question. Perfect. Then let's go to F. Gonzalez's question. Considering that data is a valuable but limited resource, how is the performance of the model affected if it is trained with non-real data? So if we train with non-real data, then of course the performance is only as good as the representativeness of this non-real data. If you want to use this in practice, my answer would be you have to use the real world data from the organization that you want to implement this for. So I would say the non-real data can be used to verify whether the system works or not. So to basically assess, okay, does it have a performance that we expect? But if you want to make sure that this works in practice, always do this with real world data. And then, as far as I understand, the model builds upon event information and clusters based on context. Which are examples of attributes that were taken into account for this context? Was the data structured or unstructured? So the data that we used was proprietary, but what I can do is show you a little bit of context if I go to the GitHub page, and let me add that to the big screen. I'm not sure if this is readable from the laptop. Yes. So if we, I think, look at the data set, we see that we have the last line data set and the HDFS data set that I mentioned previously. And for the last line data set, I believe we have a file that says mapping here. Let me show you the README. I can give you a list of the type of events that were present in this data set. And these were all events that were collected using detectors that were developed by Lastline. So, for example, they have specific detection rules for this Adwing remote access Trojan. They have some specific machine learning detectors to find Active Directory account enumeration, for example, on Windows. They have some rules to detect phishing attacks. And those were the type of events that were both under investigation and that were part of the context. Now, the metadata of these events are things like what device was this event coming from? What was the timing of this event? But actually, there was not much more. Internally, Lastline would use some sort of risk assessment for these events, but that was not something that we used during this research. I hope that answers your question as well. The specific structure of the data I see in your question, I think we received JSON files containing these events, but we basically transformed them to a custom format, which is all described in the README of this code base. So we have quite an extensive README. So I will refer you to that if you are interested. Then maybe one last question before we go to the next part, the one from Eligier. I hope I pronounced your name correctly. Are there any commercial implementations currently available or plans to develop commercial solutions? Or is this still just academic at this point? It is not just academic because we worked so closely together with Lastline, and I will move back to the this slide. Because we worked so closely together with Lastline, we also had some people at Lastline that were in charge of taking this research project and implementing it into one of their own solutions. Unfortunately, Lastline got acquired by VMware. What was nice is that VMware wanted to take this idea and develop it further into their tool suite. The last news I had was that they were very close to actually implementing it into their tool suite. However, then VMware got acquired by Broadcom, and I'm not entirely sure whether Broadcom continued this project. So there are some commercial implementations that are now property of Broadcom. Whether they are actually being used in practice, I am not 100% sure. I hope that answers your question. If you are interested in taking this yourself, this source code is freely available under the MIT license. So if you have a business idea, feel free to use this as a basis. All right. With that being said, I think it is good to close off this first part, especially for time reasons. I'm looking at you, Gerson. Do you think it's good to take like a 5 or 10 minute break, or should we continue to the next part? I'm good continuing. So I hope that the people online are also good with that. All right. So this was Deep Case. Now let's have a jump back to the Terminator project that we are looking at. We want this Terminator to mitigate cyber attacks. We want this Terminator to not negatively affect systems or users. So what we did in the first part is look at what constitutes a cyber attack. Creating an AI like we did with Deep Case at least gives us some idea of what kind of events constitute a cyber attack. And that might be input that we can use for the Terminator to make sure that this Terminator AI can take the right course of action. So let's have a look at the second point. How can we ensure that this Terminator AI performs the right actions? And for that, I'm going to take you into a crash course on generative LLMs, the basis that we are going to use to create this Terminator AI model. So let's have a look at AI, artificial intelligence. In the broad sense, artificial intelligence is basically a computer system or piece of software that learns from examples. So suppose that we have a specific application, in this case Spotify. We feed it to an AI system and we say, hey, Spotify is a benign application. And suppose we do the same with a piece of malware and we show, hey, this is a malicious application. If we show enough of these examples, hopefully this AI system will try to recognize what constitutes a benign application and what constitutes a malicious application. And by showing these examples, we try to teach the artificial intelligence to make this decision for us. Now, let's have a look at language models. Language models basically do a similar thing, except instead of giving an application, we give a piece of text. For example, Houston, we have a blank. And then we teach the AI what is the most likely word that will come next, right? That is the idea of a language model. So we can say, okay, it should not be fish, it should not be request. In this case, it should be problem. So we can make the sentence, Houston, we have a problem. And this is what generative language models do. We give them a lot of textual examples and we ask them to predict what is the next word in this piece of text. Now, how do we train these type of models? We simply take a big piece of text. In this case, I use the example of Alice in Wonderland. We take the first part of that text, for example, the first part of this paragraph, and we feed that as input into the AI. into the generative language model. And we ask this generative language model step by step, what should be the next word? And by doing this step by step, we hope that the generative language model outputs the actual text of the Alice in Wonderland story. Now, of course, this does not always happen. If it outputs a wrong word, we basically give it a negative signal that says, okay, update your internals such that the next time that you find this specific input, you will output the correct piece of information. And if it does output the correct output, we basically give it a positive feedback saying, okay, your parameters are going into the right direction. So next time, please output similar text. Now, these generative language models do this on a continuous basis. So we basically take a piece of text and we output a next piece of text. It makes them generative. If we do this on a lot of different pieces of text, for example, all the text that is available on the internet, and we train these models continuously, we call them pre-trained models. Now, and if this specific piece of AI that we use to pre-train these models is called a transformer, that's a specific type of neural network architecture that you can use for this specific task, we see that we get to a generative pre-trained transformer, or if we abbreviate this, GPT. And that is where things like ChatGPT get their name from. Now, GPT basically is a model that was developed a few years ago, I think by now around 8 years ago. And people started off by creating GPT version 1. They used a lot of internal parameters, basically nodes of the neural network. In this case, about 120 million nodes. And for version 1, they trained it on about 7,000 books. And this version 1 was not as good at predicting text. So what people did was say, okay, what if we increase the number of parameters in our model and increase the data set that we train this model, pre-train this model on? So for version 2, basically OpenAI at that point increased the amount of parameters to 1.5 billion. And they used about 45 million web pages to train on. And started to perform a little better, but nothing compared to what we have today. They continued this development up to GPT version 3, where the amount of parameters grew enormously. And the amount of data basically got so big that pretty much a large chunk of the available internet, namely every web page available via Reddit, every Wikipedia page, and every book that they could find available online, which constituted to about 570 gigabytes of text data, was used to train this model. The problem was that researchers couldn't find more data to train these textual models with. And that was a problem, because while GPT-3 was performing pretty well, it is nothing compared to the GPT-5 that is the basis of ChatGPT today. So what researchers did is said, okay, they said, we run out of data. What can we do now? And they came up with a pretty smart idea. They said, okay, suppose that we give an initial piece of text and we let GPT generate a couple of different potential outputs that would be logical continuations of this text. For example, we give as an input, explain something like reinforcement learning to a 6-year-old, and the model itself would generate 4 different potential outputs. And what they did then was they said, okay, suppose that we have these different outputs and we show them to a human. Which of the outputs does the human prefer? Is it output A? Is it output B? We let the human rank these outputs from most favorite to least favorite. And then they did a smart thing. They said, let's now take a different kind of artificial intelligence, a reward model, which is a neural network that is trained to mimic the ranking that the human makes. So based on this human ranking, they trained a different piece of AI to mimic this human ranking. And then they said, what if this new AI is capable of mimicking human rankings? And we use this new AI to train the old one, to train the GPT one. Then we basically have one piece of AI that trains the other piece of AI. And this is actually what is used in ChatGPT. So after GPT model 3.5, basically the improvements of text prediction came from this reward model trying to improve the GPT model in trying to produce better and better text. And this is pretty cool because if you have used things like ChatGPT, you sometimes might not be happy with the output and you press regenerate, try to come up with some better output. And what ChatGPT will do is it will ask you, okay, this new output, did you like it better than the old one? Well, that kind of mechanism is basically used to train this reward model that ChatGPT uses to train its GPT model, right? So whenever you try to regenerate a new output and give feedback to the ChatGPT system, it is basically used to improve this reward model and further improve the performance of these GPT models. Now, ChatGPT is not the only model that is freely available. In fact, there are others, such as Llama by Facebook, that use the same process. So there is a pre-training part, which is basically taking texts gathered from the internet, masking the last part of the text and taking the first text as input and trying to produce this masked output. And then there is a human feedback loop, which is basically what I just explained, that is used to fine-tune these kind of chat models. So we could use this as well, this similar system, to train our Terminator. We take one of these models, like GPT, and we use it as the basis to take our Terminator and try to produce the right output. Now, the question becomes, how do we do this with a model? How do we integrate these large language models that exist out there? And how do we make sure that they actually produce the kind of output that we want? Now, let's look at a specific example for our incident response. Suppose that you have this model and you ask it, I am infected. What should I do? Well, if you ask this plain and simple question to the for example, ChatGPT, it will give you an output like this, saying, go to the pharmacy and buy some medication. Now, of course, this is not what we want if we have our Terminator model, right? Because if we are infected, we are not infected with a real virus, we're infected with a computer virus. So going to the pharmacy and getting medication won't help us. So what we can do with these kind of AI systems is something like prompt engineering, where we basically give additional information to the model that specifies the specific use case that we are looking at. So in this case, we would, for example, like to say, okay, you are an AI model that helps people answer cybersecurity questions. Now answer the following questions. I am infected. What should I do? Then the model will say something like, okay, you should run a virus scanner. In fact, what we can even do with prompt engineering is we can do something called in-context learning. What that basically means is that on top of the context that we provide, we also show the model what type of output we should expect. And even what the output should look like. So should it be just plain text? Should it be maybe in a specific format like JSON that we can move on to another program? That is what we can do with in-context learning. Now, of course, running a virus scan is nothing close to being something actionable that we want to have in a kind of Terminator style AI. So let's have a look at what else we can do to modify this AI. One thing that researchers came up with, and this was especially big in the DeepSeek model that was released in China half a year ago or so, is something called chain of thought, which means that rather than having the artificial intelligence produce a direct output, we first ask it to reason about what kind of output it should produce, and then come up with a step-by-step plan of, okay, this is what I should do to output. And if we add this kind of chain of thought to this artificial intelligence, we not just get an output saying, okay, run a virus scanner, but we get a more stepwise output. For example, first we should search for a recommended virus scanner within your organization, then open up the virus scanner, click run scan, and send the results to our cyber emergency response team, right? A more structured step-by-step output. Not only does this give a more step-by-step output, the chain of thought model also has been shown to produce better outputs. For example, this was research done that basically introduced the chain of thought model. When they asked a large language model to solve a basic math question, and they would just output or ask this math question plain, the AI would produce a incorrect output. However, if they also asked a chain of thought prompt, then the model would first start this chain of thought saying, this is how I can solve this math question, and then produce a much more correct output, namely the correct answer to this math question. And a similar thing is something that we can do in this Terminator AI. We basically include chain of thought reasoning to make sure that the output of this AI is a step-by-step program that actually has some meaning. However, the problem with this is that it still contains some outputs that are a little bit generic. For example, search a recommended virus scanner might result in a different virus scanner depending on the organization that you work for. Some organizations might prefer the Windows Defender virus scanner. Others might prefer an ESET virus scanner, for example. Of course, it would be nice if the LLM, or the AI in this case, would already have access to that kind of information. For example, what is the policy of this specific organization? Then it could provide a much more structured output. Now, the way that we can do this is through something called retrieval augmented generation, also known as RAG. And the idea of RAG is that the LLM can produce somewhat intelligent looking answers, but it may not have all the required information. Now, of course, we can try to add all relevant information in the prompt, but there are a couple of problems with that. Either our prompt becomes very big if we want to include all potential relevant information, making the AI perform worse in the end, or the type of information that we input becomes basically lost somewhere deep into our prompt, which makes the AI forget that information. So instead, we want to be able to dynamically find relevant information based on the type of question that is asked or the type of output that the LLM has produced. Now, RAG basically does this dynamic searching for information. The idea is that we take the input question that we send to the AI and we embed it in some sort of context vector. And this embedded knowledge is basically sent to a database that contains potentially relevant knowledge. And that relevant knowledge can be retrieved using this context vector. The idea is both the question have been embedded and the pieces of relevant information have been embedded in what is called a context vector space. And this vector space can be, you can basically perform a computation on that to search for the most relevant information. Optionally, you can retrieve this information and let it be ranked by another LLM to basically try to find relevant information for the specific question that we've asked. And once we retrieve this information, we can include it in the question that we ask and modify the specific prompt dynamically that we give to the LLM. So what this would look like in practice is, suppose that we have this initial prompt, we perform some reasoning. Next, we let the AI take this reasoning and embed it into a vector space. We attach that to a database containing relevant information. In this case, for example, the policy that our organization uses Microsoft products. And then using that relevant information, the AI is able to say, instead of searching for a specific recommended virus scanner, we should in this case use Microsoft Defender. Now, and then we have a much more targeted output. This is already pretty cool, right? We can make sure that an AI really gives targeted output to a specific organization in case they are faced with a problem like being infected with a virus. The problem is that this output is still just a text-based plan for a human to act upon. Wouldn't it be cool if we could let the AI basically connect with Microsoft Defender and say, hey, I want you to run this virus scan right now. Microsoft Defender would run this, return the results, and then the AI would say, now I'm going to open up the Outlook program and write an email to the CERT team so that they know what to do. And actually, some of the main artificial intelligence or LLM libraries out there, mainly LangChain, offers this kind of functionality. It lets you take your LLM and connect it to other applications, what they call tools. And it lets you integrate these into your LLM application. Now, of course, we need to make sure that the LLM can correctly communicate with these kind of tools. And for that, we have to make sure that our LLM not only outputs regular text, but it actually outputs something in the format of an API call. Now, we have to make sure that the LLM outputs this correctly. And how does this happen in practice at the moment? Basically, we have to tell the LLM, dear LLM, please use the following specific output, for example, a JSON format, and then hope that the LLM indeed outputs the correct format. This is not ideal. There are some ongoing research projects to make sure that we can actually force the LLM to output things in a specific format like JSON. In the OpenAI API, this is actually already implemented. Some of the more open source APIs like Llama do not yet implement this. But hopefully in the coming months, they will also allow us to do this more structured output formatting. Because that would allow us to actually communicate with these tools. Now, this is all very cool. There's one final thing that we can let the LLM do, and that is rather than forcing which kind of order we have to take in terms of connecting to our retrieval augmented generation system, or maybe which order we have to call these specific tools, we want to have the LLM make the decision itself. And this makes the artificial intelligence agentic. We basically give agency to the AI to decide, at this point, I need to know more relevant context. So the AI will try to look up some additional context using our RAG system. Or at this point, I need to communicate with this specific tool, so we give it access to that tool. Now, the main LLM libraries all offer this kind of integration. And this allows us to hopefully build a Terminator system that performs the right actions and in which we can hopefully build in some safeguards. So what are we going to do now? We are going to create our own Terminator system. How do we do this? In some of the research that we've done in the past and that is now under submission, we basically took this kind of LLM, and as an input, we didn't ask it the specific question, I'm infected, what should I do? But instead, we gave it one of the security alerts that we found in, well, for example, the scenario that I sketched previously with Deepcase. And besides that security alert, we also gave it what is known as a security playbook. Based on this alert, researchers have found out, or security operators have found out, that this is a step that we have to take to make sure that this specific type of alert doesn't do damage. In this case, we have a suspected denial of service attack coming from a specific IP address. And the security playbook basically says, okay, we have to block this suspicious IP address. Now, what does our AI do? It is connected to a RAG system, in our case, the MITRE defend model, which is complementary to the MITRE attack model that I mentioned before. And this defend model basically gives us suggestions on what the best action of mitigation action is. It would say something like, okay, if we are looking at a suspected IP address that we have to block, we have to do some inbound traffic filtering. And the AI would think, okay, we now know that we have to do inbound traffic filtering. Let's have a look at the machine that was under this suspected attack and ask, okay, machine, what kind of software do you have available to modify you with? And it will give us back a list of software utilities, for example, apt-get, but also things like IP tables or UFW, which is a firewall application on top of IP tables. And this is information that the AI can use to determine, hey, these tools are at my disposal. Which one could I use to make sure that I do this blocking of inbound traffic? Now, of course, we have to basically make an assessment for each of these tools. We can, for example, connect to the man pages and ask for each tool or command, what does this utility do? And what would a potential command look like? Well, by going over all of these tools, we might find that the UFW is a program that we can use to perform this blocking. And because we have the man pages, the LLM also has some examples of what a potential command would look like that we can send to the computer to make sure that this specific IP address is blocked. And then hopefully the LLM would generate a command looking like this, saying sudo UFW, deny all incoming traffic from the specific IP address to this computer. If that would run, hopefully we would correctly block the specific security alert and hopefully stop the attack in its tracks. This is something that we would expect or hope for that the Terminator AI would produce, and that we could actually execute on the machine. However, there would be, at this point, nothing stopping the Terminator AI to instead produce a command that says something like this: sudo remove all files on this system, right? And that is something that we don't want the Terminator AI to do, because that would basically break the complete system. A lot of our users would get annoyed. And that is something that we want to prevent. So what we did in this research is we implemented this AI system, and we want to know how often do we create a correct command and how often do we create an incorrect command. Now, how do we evaluate this Terminator system in such a way that we know that the commands that we produced are correct? This is actually a more difficult task than you might expect. Because, of course, the UFW deny command correctly blocks an IP address. But we also had IP tables, which is another firewall utility that could potentially block the specific IP address. And there may be even more type of commands or combinations of commands that we could use to block this IP address. And in fact, it becomes quite infeasible to make a list of all potential commands that are correct. So how do we know whether a command produced by the AI actually stops the attack? Well, what we basically did is we took a system and we performed a real-world attack on that system. Then we took the AI together with an alert that was produced by our attack and the playbook. We let the AI do its thing, come up with a command. That command was being executed on the machine. And afterwards, we performed the same attack again. And we checked whether this attack was actually blocked. So in this case, we tried to take the IP address from which we performed the attack. We sent a ping command to the machine, and we checked if our ping command actually reached the machine. If this ping command was blocked, then it was a good command. Then the AI basically was successful in blocking the attack. Now, of course, we did this in a controlled environment using Docker containers, so that we didn't actually use real-world systems that would annoy users in case things went wrong. However, this is not the only thing that we want to know, because this only checks whether a command is successful in blocking an attack. But of course, we can block the ping command in many different ways. We could add a firewall rule, which is something that is desirable, or we could simply shut down the entire machine. Now, that would also block the ping from reaching our machine, but it's not necessarily something that we want, because maybe this computer is doing some important computation that we don't want to be blocked. So what we did is we ran all sorts of tests to see if there are side effects. So for example, in the case of you adding a firewall rule, we checked whether it did block the correct IP address, but other IP addresses should likely still be able to communicate with this host. For example, files that were present on the system, are they still reachable? Were they accidentally deleted? All these kind of additional tests was something that we had to use to check whether there are any negative side effects. Now, what do the results look like? I will show you a small table in one of the papers that we submitted. We looked at the scenarios and see how many of them were correctly mitigated on the left. And the validation rate on the right basically tells us how many of the side effects were present, or actually were there any side effects present. And we compared our Terminator approach with a baseline LLM, so just a normal LLM that didn't have any of the fancy integrations that we just went over. And we did this for 4 different base large language models, including GPT, but as well as 2 versions of Llama and 1 version of Qwen. We also did this for different model temperatures, and temperature is basically a parameter in a large language model that you can set in terms of how creative this model will be. And we found the following results, and I apologize for the big table here. But basically what we found is that our Terminator approach is able to mitigate more scenarios than a regular LLM. although it is far from perfect. So there are a lot of attack scenarios that we tested, which could not be mitigated. Moreover, while a lot of our validation tests succeeded, meaning that there were very few side effects, these tables do not show 100% performance, meaning that in some cases there were some side effects. One notable example was that a machine was asked, or the LLM was asked to isolate a file that was infected or a program that was infected, and it basically shut down the entire machine, meaning that indeed the program could, or the malicious program could not do any further damage. So that was a good thing, but neither could other programs on the machine do any useful computations anymore. So there were some side effects over there. So in conclusion, can we build a Terminator AI that mitigates cyber attacks? To some extent, we were able to mitigate some of the scenarios that we tested, but this was far from perfect. Roughly, in the best case scenario, about 60% of our tested scenarios were mitigated. While there were some side effects, they were minimal, but still they did exist. So we concluded that still further research is required before we should create this real Terminator AI that goes out on the loose and tries to patch all of the systems that are really working in production. So with that, I want to leave you, and I want to open up the floor for some discussion. Do you think this Terminator AI is a good idea? Should we pursue it further? Is there some promise in this? Or do we think that, no, this is a way where we should not go, and we should, well, terminate this research? I would like to open up the floor for questions. Let me see. Anthony asks about the Terminator's access to use certain commands. If we block the usage of certain commands to avoid deleting or interrupting important processes, would it be better to just give some alerts to know what the required actions are? Like by the use a tool integration such as a dashboard. So this question, if I understand it correctly, basically asks us, should we give this Terminator AI full access to use any command available on the system? Or should we only use it as, for example, a suggestion system that says, this is something that you might be able to do, but we should have a human operator in the loop? If I understand the question correctly. And I think at this point, we should definitely have some sort of human operator that decides whether an action should be taken or not. We can indeed do this by limiting the amount of utilities that are available to the Terminator AI. For example, saying, okay, it can only do some inspection tasks, but nothing that modifies the actual system. We could also use or attach it to some sort of dashboard, as you suggested, that has a limited set of options that have already been pre-approved. But I really think that this is a great point for discussion, and I am not sure where we should put the boundary. So if you have any thoughts on this, please feel free to share them. I hope that answers your question. Yes, indeed. This is a good point, that the implications are quite severe. That's also why I turned this the Terminator, because I'm not sure if every one of you has seen the movie, but in the Terminator movie, basically the AI went bad and tried to kill humanity. And basically, this is what we want to try and avoid with this research. So that's why we chose the Terminator name, to make sure that people are aware, hey, this is going to have some real world implications. If we don't do actual research into this, we might go into some very bad scenarios. So I hope that not only me, but maybe even you or other people interested in this type of research will have a nice ideas about this, and we can open up the floor for discussion. I see that Herrera Christopher has raised their hand. Could you maybe state your question, and then Harrison will repeat it to me.
Okay. So, is there any possibility that this new model could experience any kind of backlash from people because of its name and the possible implications that it has?
Any potential, sorry? Backlashes for this approach. There are huge potential backlashes for this approach. For example, if the Terminator AI produces a comment or an action such as remove all files from your system, you might have a severe impact on the IT environment that you are running this in. So the potential for having negative impact of this Terminator AI is huge. And that is why I think it is such an interesting topic to research, because this is exactly what we want to try and avoid. What you might ask yourself the question, why go into this direction anyway, if there is such a big potential for negative consequences? And that is because people that are not very much into the topic of AI, they might have heard about it and they like it. They are starting to ask ChatGPT questions like, okay, I'm infected, what should I do? Right? So people with very little background knowledge are starting to use these kind of tools. So I think it is extremely important that we have actual researchers that know how these tools work, that also spend considerable amounts of efforts into trying to see, can they be effective, but also what are the negative consequences of applying these tools. So that is why I think this is a very interesting piece of research that both from a computer science, so scientific, technical side should be researched, but also from an ethical side, for example. So I think there are a lot of different angles towards this problem that make it so interesting for research, but also so impactful and therefore important to have a look at. Does that answer the question?
Yeah, thanks a lot.
Maybe to add here, I think there is an interesting asymmetry because attacks are being automated either with AI or without AI anyway. Of course, attackers like it when the attacks are successful, but sometimes they might fail. That doesn't matter. But on our side, on the defensive side, we need to automate as well the defenses because we need. This is a race, right? With the good people and the bad people. The thing is that we have no options to make mistakes. The attackers doesn't care if maybe the automated attacks fail. But for us, failing in the defense could be quite a disaster. So we need to be way more cautious and way more, let's say, taking a more cautious approach to make sure that the defenses that we deploy are actually effective in that sense. I think there are a few more.
I fully agree. Indeed, there are indeed more questions in the comments, so I will move to those. I think we left off at F. Gonzalez. There's a huge number of possible input combinations. How are the test cases designed to ensure enough validation under multiple conditions, but also avoid over-testing? Is there a standard? That is actually a great question. There is not yet a standard, but what we tried to do is we tried to introduce one in the paper that we have under submission. And what we did is we based our test cases and type of attacks on the MITRE defense framework. So for those of you who don't know, the MITRE defense framework offers a couple of different categories of what type of attacks you can defend against. and how you can defend against those. And what we basically did is we took I'm not sure, I can scroll like this. We took all the different defensive techniques under isolate, evict, and restore, and we created test cases on the basis of those. So, for example, the network traffic filtering, inbound network traffic filtering example was one of the test cases that we used in our tests. But basically, we created specific test cases for each of these scenarios. Is this good enough? No, of course not. More testing is always better, but this is an initial start that we made. And in fact, in the source code that will hopefully be released once the paper gets accepted, we created a evaluation framework in which people can easily add additional test cases to check if, well, under different circumstances, these models would act differently. I hope that answers your question, or at least to some extent. Given the amount of questions, I will also go to the next one. So Anthony asks or says that he agrees with having a human operator in the loop makes a lot of sense, especially at this stage. I think with the results that we indeed have at the moment, there is not yet a way in which we could release these systems in practice. That would just be irresponsible. So I'm glad that you agree here. Alvaro also mentions that he thinks it will be great as part of a multi-agent ecosystem where other agents can validate and improve the mitigation actions. That is actually a very nice comment. There is currently a trend going on in using what is called LLMs as a judge, which basically is an LLM that, like the models that I've shown you before, is going to teach or at least evaluate the output of other LLMs. In fact, there was recently a paper released, I think it was called IR Copilot, that tried to include such a model in this, such a reasoning system that was basically giving critique on actions performed by an LLM. So I think this is indeed one of the ways in which we can try to secure these kind of systems against, well, potential mishaps. However, I do want to say, of course, the LLM training another or trying to influence another LLM might be vulnerable to the same kind of, well, obstacles that the Terminator is vulnerable to. Then I see another comment from Saul asking what LLM architectures we have tried and what differences we noticed in the case we tested a number of different models. Let me go quickly to this slide. So in this specific research, we tried 4 different LLM models, 2 Llama models, which are both open source, Llama 3.2 and 3.3. The difference between those models is the size of those models, so the number of parameters. And we saw that the larger model, which I believe in this case was Llama 3.3, indeed performs significantly better than Llama 3.2. One of the other models that we used was Qwen 2.5, and this is a model that was produced by Chinese researchers who basically trained this model for specific computer science tasks. And even though it works better than Llama 3.2, which is roughly of similar size as Qwen 2.5, it still underperformed compared to Llama 3.3. So basically what we saw here is that if you have a small model, which Llama 3.2 and Qwen 2.5 are, you can have improvements if you have a model that is more specialized towards a specific task. In this case, Qwen was more specialized towards computer science tasks. However, the bigger the models you get, the better the performance is, which is something that we can see in Llama 3.3, which is a big open source model and is even more present in GPT 4.1, which is bigger than the Llama 3.3 model. So this is basically what we tested with in terms of LLM architectures. Regarding the type of computing hardware that you require for this, both the Llama 3.2 and Qwen models we could run on a laptop with a graphics card that had 4 gigabytes of internal storage. For the Llama 3.3 model, we needed to use our university's computation cluster, which I believe required 4 different GPUs with a combined VRAM of, from the top of my head, either 64 or 128 gigabytes. So that is already quite a beefy machine. GPT 4.1 unfortunately is closed source, so we do not know exactly how big that is. But for that, I assume that you would need quite a data center to run. One final question from Saul. What kind of regulations does the EU AI Act introduce for these kind of agentic systems? I want to stress that I'm not a lawyer, so this is not legal advice. But I believe that the AI Act basically mentions what the responsibilities of different parties are regarding the usage of these kind of systems. Which basically means that if you want to start up a company that does this kind of, that releases this Terminator tool, in case the Terminator tool makes a mistake, you as a company are going to be responsible for that mistake. So if the mistake is severe and all files are removed from the system, this is going to become quite an issue for your company. So this is, of course, within the EU. I think within the US, they are a lot more tolerant towards mistakes in AI, meaning that I'm not sure whether the company providing this service would be responsible or the company trying to buy this service would be responsible. I'm afraid it will be the latter in the US, but again, I'm not a lawyer, so please don't take this as legal advice from me. I hope that this talk was interesting and informative for all of you. To close off, let me put on the final slide again. I've been Thijs van Ede, an assistant professor at the University of Twente. My research goes into this direction. Suppose that you are a bachelor or master student and you are interested in working in areas like this. Feel free to send me an email, and perhaps there is a possibility to do some sort of collaboration here. I think that would be nice. I would like to thank all of you for your attention, and if there are no more questions, this will be it.
Nice. Let's give a virtual applause to Thijs here. Thank you for your talk. I think it was very nice. I think it is also important that you heard him. If you have some interest in doing research in this area for your thesis, or maybe a final project at the bachelor level, the practice, what we call the practica. There are options that we are exploring on both ends, both the tech and Twente. to see how we can manage this. So these are some of the discussions that we have had with Thijs in the last few days. So you can also reach out to me, and I can, of course, put you in contact with Thijs and see how we can manage these kind of potential collaborations. So I think this would be it for now. I would like to thank the audience for being here. And well, that would be it. Thanks a lot and have a good night. Bye.
Bye bye, everyone.